But yeah, welcome everyone. Nice to see a full house here to talk about heat pumps. So this is I think the first time at Automated Buildings we've had a session just dedicated to heat pumps. But I wanted to do a session like this year because we're starting to do a lot of heat pump projects. And we're learning a lot, but we're also getting called into a lot of heat pump projects that don't work. So my name's Brad White. I'm president of SES Consulting. We do a lot of decarbonization work, recommissioning work. So we design a lot of heat pump systems. We recommission a lot of heat pump systems. And we're seeing a lot of heat pumps that just aren't performing the way they should. And I mean, I was going to tell a little story of just to give an example. I'm looking at an email thread for a project we're working on right now. It's first school. We were doing a recommissioning project, kind of unrelated to a new heat pump they just had installed. And we come in, the operator's like, yeah, it's all working. We just had it commissioned. It's brand new. It's working. And I was like, well, why isn't it on? He's like, oh, well, we had a pump failure last week. I was like, okay, when's that going to be fixed? They're working on it. We're waiting for a part. And then the next day we get forwarded another email chain from the controls contractor that is, well, actually, we can only get the heat pump to deliver 105 degrees Fahrenheit water. It's supposed to do 120, but the reset signal is 100%. We don't understand what's going on. And actually, only 2 of the 5 heat pumps will even come on. So I'm like, all right. So now we're a long way from the project that was supposedly fully commissioned to a heat pump that is not working at all. And then, so the question is, well, who's over, is this still being commissioned? And well, no, commissioning's done. Now it's the control contractor trying to troubleshoot this with an operator who's operating 20 schools. Well, where's the consultant? He's like, well, no, the project's done. They're gone. All right. So now we're getting pulled in to help sort this out. Another project that we actually designed ourselves, brand new essential heat pump for a building, office building, I think 200,000 square foot office building. It's a 200-ton heat pump. Lots of conversations with the distributor. We're designed around a particular product. Great, it's all designed. We need 130, 135 degree water. Yeah, no problem. Unit's rated for that. Fantastic. Unit comes to site. Startup tech shows up, sets it to 115. Okay, sorry, we need 125. He's like, no, we don't. The unit actually doesn't like 125. We really recommend you don't push it past 115. So this is the first time that information had been communicated to us. Now that the equipment's actually on site. And so, okay, now we got to figure out how to deal with this situation. And that's a couple of stories that I have, and I could probably spend the whole hour just telling stories of things like that we've run into in heat pump projects. But what I want to talk about today is how do we get past that? So we've got a great panel. These guys know heat pumps. We're going to talk a lot about how to get heat pump projects to work properly. We're doing a lot of them now. I mean, I'm in Canada. We're doing a lot. I know there's different jurisdictions in the US that are doing lots of electrification projects. There's a lot more of these things out there. And I guess the first question too, is you might be saying, well, what's a giant heat pump? And this is actually the first thing we talked about when we did our planning calls. What do you actually mean by giant heat pumps? Do you mean 1,000-ton industrial scale? No, I mean not split units. So we're not talking about little mini splits or even really VRF systems. We're talking about central air-to-water heat pumps. Think about 100-ton, 200-ton kind of system. That's the sort of thing that we want to talk about. Air-to-water, water-to-water, heat recovery chillers, that kind of thing. So we're going to go deep on heat pumps. I hope you have lots of questions. We're going to make lots of time for questions. But to start with, I'm going to give each of these guys a few minutes to kind of tell us who they are and a little bit about what they know about heat pumps and what they see is going on in the market. And so let's just get started here on the end. Dan, why don't you get started?
Thank you. Thanks for being here and good afternoon. My name is Dan Gentry. I work at Train up in La Crosse, Wisconsin. I started in the industry about 15 years ago at Multistack, which is up in that area as well, just down the interstate. doing chiller product support sort of stuff. So I'd have a lot of experience with heat pumps and heat recovery, air-to-water heat pumps. They've been doing that for a long, long time. And then I took a role as a sales manager for Canada, and I was up there for about 3 years, working on a lot of similar projects as you're talking about over here, especially up in Vancouver and in Quebec, where electrification has been going on for a long, long time. So I gained a lot of really valuable experience there. Came to Train about 8 years ago in our chiller product support group for centrifugal chillers. So again, a lot of knowledge and experience with centrifugal compressor chillers. Electrification was really, from our company, was getting pretty large when I started, and with my experience with heating essentially at my previous employer, I got very involved with a lot of the heating applications that we were doing now with centrifugal chillers. For the last 3 years, I've been in our applications engineering department, which what we do is we really look at systems. So we have a broad and general understanding of products and how they work and how to integrate them into systems. So mainly what I do, I would say over 90% of the work I work on is related to heating or electrification. A lot of it's new designs, new construction, so working with consulting engineers to lay out optimal designs, picking water temperatures, delta Ts, pumping configurations, talking about redundancy and what do we do for cold climate heat pumps, getting some large heat pumps like heat recovery applications for call it high tech, like semiconductors and data centers and that kind of stuff, where we're talking about now thousands of tons as opposed to hundreds of tons. And then we also get involved with, say, problem jobs or jobs that are having issues, trying to solve those, working with technical support, engineers in the field, and coordinating to figure out what's going on, what needs to be fixed, how do we fix it. I would say, in a nutshell, that's what I do.
I have some follow-up questions, but I'll let James go.
My name is James Murphy. I'm the sales manager for the equipment division at Long Building Technologies in Denver, Colorado. I've been in the industry for about 25 years, and mainly dealing with heavy equipment, energy recovery chillers, air handlers, that kind of thing. Just kind of wanted to bring a unique market to the panel, meaning that we are a low temperature and a high altitude climate in Denver. And so there's a lot of challenges with air source heat pumps in our market, and we run into a lot of pushing the envelope of what air-cooled and even water-to-water can do in our climate because of our low temperature and also because of our altitude. We run into a lot of the similar problems where we're not making enough heat. But the biggest one we run into is the heat pumps don't turn on when we need them the most, which is problematic. And having a plan for that, because it's a big challenge, but challenges can be overcome. It's just the hard no's we have to think about it ahead of time, and we have to get way ahead of our projects, where we're having these discussions with the owners and the people who are driving the drive to clean heating and clean energy. And if we have these conversations way ahead of time, then there's an acceptable amount of risk we can all kind of go into the project. But if we wait and wait till it's installed or something like that, a lot of people might have objections to those risks. So that's kind of where I'm coming from, and hopefully we'll have a great discussion today.
Thanks, James. And Mihir.
Hey, my name is Mihir Nanthakiliar. I'm with Johnson Controls, and I've been in our chiller division for a long time. Both in the application engineering team and as a regional sales manager, which the region included Canada, which is obviously very, very heat pump focused. I've been, a lot of our product line has lent itself to the super large heat pumps that, the water to water and so there's a lot of experience, on the campus and district energy side of those designs and challenges that can go on. But for the last couple of years, as the decarbonization trend has really solidified and required the need for air source heat pumps, a lot of my exposure to these projects have been in the kinds of products you're describing, not quite that big, but certainly not buildings that can be served by mini splits. So With that, I'll, let us maybe move on to the next stage of the questions you had.
Sure. Yeah. Thanks, guys. So yeah, if you have questions, there is a mic in the middle that we would encourage you to use, but if you'd prefer to just yell out, you can do that too. But to get started, I think maybe go back to something you said, Dan. I mean, you talked about getting involved a lot in troubleshooting. And I kind of want to dig in to kind of what you're actually seeing. Like, what sorts of things are you troubleshooting, and like where do you see those issues? Like, what's the underlying source of those issues in your experience? Like, what are you running into most often?
Yeah, I guess I would say probably the biggest thing that I personally see most often is related to pumps and pump control and the pumping configuration. Meaning, like, if we take modular chillers for an example, I've done a lot with modular chillers. Getting the pumps, say, sized large enough, a lot of times those, we've seen that they're a little bit undersized, and that can be very problematic for modules that are opening and closing valves and changing the flow rates. Also, the speed of control for the pumps. So if these valves and modules are opening and closing at a relatively quick rate and the pump can't speed up fast enough, we're going to lead into a lot of flow-related, depending on if it's heating or cooling, low suction, high temperature related sort of trips. Seeing variable primary flow try to be applied when there's not enough turn down for the unit, or maybe sometimes no turn down. A lot of times, like decouplers are way oversized, so we have, say, some poor temperature control. We may see even minimum flow bypasses, VE'd out of designs. We've seen that several times. Another thing we see is with, BAS controls, trying to control a unit too much, and this isn't just modular now, this is kind of any unit. Even just recently, I've seen a couple jobs where the system level temperature has been made, and then the automation system just shuts off the heat pump, shuts the whole thing down. And several times I saw some heads shake, and it sounds crazy, but one thing I try to talk about is let the unit controls do what they're supposed to do. Give the heat pump the temperature it wants and tell it to go, and let the unit controls control the unit. That's probably two of the big things: controls, and then like the pumping controls and configuration.
That jives with my experience as well. And I get, one thing I kind of boil it down to often is like, heat pumps are not boilers. And a lot of the things you can get away with doing with boilers, like variable flow and aggressive temperature resets, and like they just don't work with a heat pump. It's a fundamentally different piece of technology. And I feel like, at least I'll speak as an engineer because I'm an engineer, but I feel like the engineering community is just starting to realize some of that now, and almost thinking like, well, we can really optimize this thing, same way we optimize boilers, and then not realizing.
I totally agree with that. I actually just recently made a slide for a PowerPoint that said heat pumps are not boilers.
Well, and they're
so
finicky.
We have to think about that.
So like heat pumps are kind of snowflakes. Like they like a temperature that's the right temperature, and they like a flow that's the right flow. And if you get too far out of that, like the thing just shuts down, and then you've got a problem. No. But I don't know, James, does this sound familiar to you? Or?
Yeah, and a lot of ours is actually a little further upstream than actually when the install happens. Where we run into problems is we're designing on the ragged edge of the equipment, right? We're always pushing the envelope, and when someone, to your point, says that they can get 120 or 125, and it's just outside the envelope, heat pumps don't like to operate there. They don't like to operate outside their envelope. They like to be nestled in the middle. And we all have to be ahead of that and honest about what they can and can't do, because a bad job is going to make it miserable for everyone involved. And we were really trying to force these heat pumps into the high altitude and into the high water temps have really been challenging because it just puts it just outside the operating envelope. So where we've run into problems is when we're really trying to push it and not having that conversation. If everyone's aware, hey, we're pushing this, we're trying to do something, then everyone's kind of on board for the problems, right? But if we're kind of pushing it and that doesn't get passed all the way through the project, then we really have problems at the end. And that's what we want to avoid.
I was going to say, like, what's the solution to that? Is it to not use heat pumps? It sounds like you're still saying you can use heat pumps.
Yeah,
but
I will say it's a challenge, right? And as long as we're upfront that this isn't a cookie cutter job, it's probably going to cost more, or it is going to cost more. It's not probably. It's going to cost more, but it cost and return on investment, that's not why we're going to heat pumps, right? Everyone in the project has to be bought in that this is the right choice for the environment, the right choice. That's what pushes these jobs forward, not, well, it's going to save you a bunch of money. Because if that's the case, you're probably not going to succeed, because that very rarely happens. And as long as everyone is kind of working towards that common goal, the cost, the design, so like a redundant, maybe like a dual fuel option, when it gets really cold, all of those are things that we'd bring to the table, but add cost to the job. They're challenges, nothing's something we can't overcome. It just brings a lot of stuff extra to the table that we needed.
yeah.
Another question for Dan. You say valves reacting too fast or too slowly?
I would say, so in some machines, the valves and that's called a module, can open and close really fast. And if the pump speed doesn't speed up fast enough, we can have an issue. Like if you have one module running and the second one turns on, valve strokes open, but the pump speed doesn't catch up quick enough. Now you're flowing half flow through a fully operating module and one that's not.
And the other way too. Yep.
So would you speed up the pump before that?
That's something you can do. There's there are a lot of different pump control strategies, and some of that also depends on how you're measuring. Are you measuring a differential pressure? Are you using a signal from a controller? Are you using a flow meter? So it's kind of, there's a lot, and all different manufacturers have different options and capabilities for control. So it kind of, when you get in that kind of, it depends on the product sometimes.
Again, sorry, just taking a step back, is this discussion apply equally to water source heat pumps as it does to air source heat pumps, or is there different?
Yeah, I would say it applies the same. It's just the different, we're talking about either chilled water as a source or air as a source, but I would say that the conversation is applicable to both for sure.
Yeah,
I think the water side solves some of the problems, right? Like especially at altitude, it solves a lot of our problems. But
you're not as ambient temperature.
Yeah,
dependent.
It brings a whole new slew of problems. Well, all of that, and also our heating load through, like if you look annually, is way bigger than our cooling load. So if you do a ground loop, you have to size for the heating load, and that might be an extra 1,000 boreholes or whatever it is, and it can drive cost of the job. Or there's other strategies you can use to reduce it, but that misbalance in your cooling and your heating is one of the problems that water to water bring.
I've seen a lot of fields freeze up after a couple of years,
right,
because they were taking out way more heat than they were putting in, and that hadn't been accounted for properly. And it works fine for a couple of years, but eventually, that ground temperature gets lower and lower, and then usually they give up at that point, and then boilers get turned on, and that's it.
Good case for hybrid geo.
Yeah, we do a lot of hybrid systems, but they come with their own challenges, because I see a lot of hybrid systems where the first time the heat pump runs into an issue, that's it. Nobody bothers to troubleshoot it because the boiler kicks in. Everyone's still comfortable. As far as the operator is concerned, it's better because you don't have to worry about this heat pump anymore. But the owner is, the whole reason you spent $1 million on this thing that's, sitting there, as a brick now.
We do a hybrid a little differently. We've used air source heat pumps and water to water, and then we, like in the shoulder seasons when the air source is super efficient, we use that to inject heat back into the loop so that we can reduce the loop size. So when it's 47 degrees outside and everyone's air source heat pump is kicking butt, then we actually inject heat then in like the October and the September and that range, and raise that loop temperature up to try and equalize out that load.
Like charging a battery.
Yeah, exactly.
Like charge a ground field?
Yep.
Yeah.
Yeah. And it's a way to, so you're still all electric, you're not going back to the boiler, and you can kind of save that loop a bit and prevent those after 2 years, 3 years, it freezing up or getting too cold.
Yeah. This is great discussion. Any more questions from the audience right now? Okay, Mihir, maybe I haven't heard from you in a minute. Why don't you jump in, and do you have, talk about this from your perspective. Are you seeing the same issues? How are you getting past them?
Yeah, I think flow and managing multiple pieces of, let's say, multiple refrigeration piece of equipment, right, is where things start going a little bit different, right? When I hate, I always say a lot of these modules are marketed in a way that seem to indicate to a consulting engineer or contractor that these are plug and play, right? You just take it, stick it, but it's not a boiler, right? It's not just a magical piece of, equipment that's just going to be carbon-free heat. It requires design, thought, and it's, unlike even, let's say, a chiller or a boiler, which even those aren't plug and play, but generally you can put a chiller in a central plant, give it a set point. It's got a very wide range of turn down it can do. It generally has a very similar pumping range that it will operate in during its load or its seasons. Whereas, let's take the water-to-water heat pump, when it's serving a chilled water loop, it'll have delta T of 15 degree on the chilled water with, whatever load, and in the geo field application, you might ramp that rate up to get, a tighter delta T when you go into the geo field. Because these pieces of equipment are now multi-mode, there's a heating only, there's a heat recovery, there's a low load, a high load, a what happens when I stage from one chiller at 100% to now my plant needs 101, so now two chillers or two heat pumps are at 51% or 49. Do I know what I need to do in terms of ramping up a pump, bypassing that, then switching over to two? Is that sequence existing? Because again, it's planning through before we start putting things on drawings. What is my plan for this thing, not just on the design day, because, again, standard chillers, standard boilers, design day, and then you just turn it down. It's pretty straightforward. But when you have different modes that require the equipment to do all sorts of different things year-round, do I have a plan for that? Have I thought through what's going to happen to that piece of equipment when, when I'm in a shoulder season and I need to use or charge a loop or a field, which is obviously, from an engineer's or a consulting engineer's standpoint, not as easy as just saying, give me your 4-point rating, stick it on the drawings, and I can go. But it's why I think, asking those questions from the consulting engineer side to say, well, give me this is what I expect to happen in spring and fall. What will the heat pump system do if I ask it to do this? This is what I expect to happen in winter. What will the heat pump system do or the equipment do? And catch these things in design before, it's 6 months later.
I will say, as the consulting engineer, that information is often hard to get from, because we're often going through distributors. Mm-hmm. They don't know. You ask them questions about how this heat pump actually works, like the internal control sequence. They don't have no idea. So, okay, who can we talk to? And if you're lucky, you can get to that guy that actually does know what the internal sequence looks like. But some products are better than others. But man, that's hard information to get. And I think that's a big part of the reason you see these control sequences that are trying to control the heat pump, because they're well, that's what we know how to do. So I think that that's one thing I would love to see the whole industry do better, is just close that information gap so that the consulting engineers can get that information, and the information can kind of flow both ways between. Yeah,
I would say to that point, I found when we do have time, when we do sit down with the consulting engineer and go through what the internal unit controller sequence does, they're very appreciative, and I think it's usually a pretty enlightening conversation, and it could make their sequences a lot easier because they just don't know what the heat pump itself is doing. It's if the heat pump, if I just have to really give it a temperature and tell it a mode,
it makes your job easier.
That makes things a lot easier.
Well, and it's going to make the equipment work better.
Right.
And so it's I would love for those conversations just to become standard. Question. Yeah.
So who's been owning the PID? Who's generated the control company? Is it the equipment manufacturer? Is it the consulting engineer?
Yes. Well, I think we've all been involved in jobs that each one of those has taken the ownership of it. And I mean, I kind of said it at the beginning. It's more of a team approach. You need the TC, you need the manufacturer, you need the contract, you need everyone kind of on board, the engineer and everyone on board moving forward, or else it's about communication. And it could be any one of those, but as long as everyone knows what everyone else is doing, I think it'll be fine. But what happens is it's siloed so much that we run into problems because of the silos. So I don't know if one is the right answer, right? I don't know if it's the manufacturer or if it's the TC. It's all of them together has to be part of it. I think is the most important part.
I have a question as the consulting engineer designing these, because it sounds like, we aren't getting maybe all the information, but what is like something you wish that we would do differently, or information that we would ask for or provide that would allow you to deliver the product we're actually looking for?
Well, I think so. When I mentioned that there are multiple modes of operation, right? That you're going to give it, a different flow in a different season, a different temperature in a different season. If it's, the air source heat pump might be a chiller in the summer, it might be a, heat pump in the winter. And if it's a heat recovery style, you might have two different flow rates or two different temperature profiles. Understanding what your plan is in this design for all those seasons is really helpful, because we might be able to say, hey, that one design point is at the edge of our operating map. We wouldn't recommend doing that. Or, hey, if you do that, you're not going to be able to unload to 30% or whatever. And then from there, you can say, okay, well, that's great to know now. I'll either have, some storage to take care of that, or I'll have another piece of equipment to take care of that, or I'll, do a hybrid electrified and gas solution to manage the ultra high altitude, low ambient scenarios that this won't solve the problem for.
I think the other thing is, a lot of times you guys, as the consulting engineers, are managing the expectation of the owner and the architect, and that very rarely is, their expectations very rarely rely in reality. Sorry if there's any architects or owners in this, but what happens? but what happens is that they're expecting one thing, and the team can only deliver another. And as a consultant, getting those to kind of be as close as possible, I think, is where we have the most success.
I was going to say, try not to get too blinded by a certain technology or temperature, compressor type, or whatever it is. We just want to, what I usually try to ask is, what are you trying to accomplish? Don't say, I want this piece of equipment, I need this temperature. What do you need to do? And then we can help navigate what products and systems and all that kind of stuff looks like to meet those needs. And that includes a load profile and minimum loads and that kind of stuff too, to
That's really
address the
helpful,
unloading.
Because I think oftentimes we'll send you okay, here are the temps I need at this outdoor air, but we won't tell you this is the system and this is its purpose. I've actually had a manufacturer tell me just don't do variable flow. Just stop it. You guys have screwed it up so many times, not us specifically, but if you can just do constant flow, just do that. Is that aligned with?
I mean, I wouldn't just go out right now and say that, but I have heard that many times.
It's not a terrible idea.
I get a question, maybe here you were touching on this.
Okay.
Is there other systems that kind of go hand in hand with these giant heat pumps? Do you need a buffer tank? Do you need some type of volume in the system to...
System volume is a huge issue.
Yeah.
How is that factored? Clearly, when we're selecting a piece, I'm not I got 5 miles of 12-inch piping.
Yeah. So, if we're kind of centering the conversation around air source heat pumps, they absolutely need a lot of volume for a couple of reasons. One, the modularity of it, right? You're talking about, let's say, 30-ton or 40-ton or 50-ton blocks that build up your capacity. The other thing is, you've got a concern about defrost, right? That where, you could have in the 20 to 40 degree Fahrenheit ambient range, a large percentage, 30% of your units may not be heating or refrigerant circuits may not be heating at that moment. Thermal storage certainly helps with preventing coils from just suddenly seeing a huge drop in set point or supply water temperature, because you've got some of that buffer built into the system for that when that number of units go out of heating and go into defrost and back.
Yeah, if you watch like temperature trends in a unit when it goes into defrost, like you can see it. Like it's very noticeable when the supply water temperature change.
Yeah.
If you don't, especially if you don't have enough system volume.
From like a performance standpoint, I mean, knowing that we're going to see that drop in supply water temperature, should you be pairing a 2,000-gallon buffer tank with
But
the system?
I don't think we can say yes. If you have huge pipe and there's a bunch of volume in the system, then no. I think it's more of the gallons that's available to, or liters for our Canadian friends, that amount in the system, then you might not need as big a buffer tank. Maybe you could get away with a 500, or maybe so it is definitely a volume calculation, and it has to be the volume available to the device, right? Like if it's valved off, you can't count that volume, right?
It's hydronically isolated in a different loop, it's no good. But that's part of our design process. Like we talk to the manufacturer, like what's minimum system volume, and then we look at the pipe lengths and the diameters, and like, okay, we need 1,000 gallons, 500 gallons, whatever. I mean, that is part of the process for sure.
So, cooling is important, but heating is more of a code requirement more than cooling. So, given the fact that at times we have unusual weather, like what happened in Texas a few years ago, is there a discussion about any kind of a backup or how we handle? Because we can design to 1% temperatures or 0.2% temperatures. Is there any kind of recommendation as far as heat pump system? How do you design for those conditions where?
I think it comes back to the expectations, right? Like if you talk about the risk with the owner, are you okay, Mr. Hotel owner, if it's -5 outside and your heat pump doesn't work, are you okay sending them to another hotel, right? Like those are the acceptable risks. And then if you have those conversations, then you can go straight into, well, if that's not acceptable, then we have to have a backup, or we have to have a dual fuel, or we have to have, you've got running the same thing.
That, or, like you mentioned, maybe at -5, you're at the edge of producing 120 degrees, so you can't do that. But I can add some heat with 110 degree or 105 degree supply water. I'm back toward the heart of my envelope. Can my air side have an electric, element in there to add a few degrees to the air once the heat pumps rejected whatever heat it possibly could, right? Having a contingency plan for that. I guess what I'm saying is, if the difference between the 1% and the 0.2 is 20 degrees of ambient, that's a huge D-rate on an air source heat pump. You might double the amount of equipment on your roof. That could be solved maybe a little bit differently, potentially a little inefficiently, but obviously the number of hours that exist between that 1% day and the 0.2% day are so small in the life cycle of that building.
We are, we're doing like high level feasibility studies. Like, our rule of thumb is, I usually say, want to size a heat pump, like if we're doing like a retrofit, to be like, 50-60% of the peak load. So let's say your design loads at whatever temperature, 0 or 17 Fahrenheit, wherever you are. It's sort of 50-60% of that is what my heat pump is designed for, and then I assume any hours beyond that is probably going to be my backup source. But that usually covers like 80% of the energy use, because there's so few hours spent that and especially if you're trying to optimize the cost benefit of your system, like that's kind of where we found the sweet spot to be. And that, that full load, it's very expensive to do a full heating load with a heat pump, and we rarely do it.
To build on that, if you're using a device that's a simultaneous heating and cooling, or like a crossover where you're doing both with the same piece of equipment, if you size it for the peak load, you're probably not going to hit your cooling load, and you're probably not going to be able to unload. And then, so do you use the modular design and only like 7 are in heating and 3 are available for cooling? But what that does when you kind of lump off those those extreme hours, it helps you properly size the heat pump so it operates the most efficient, and then we can work on being as efficient as we can with our alternate source.
Yeah.
Brad, I'm really glad you guys put this together. You're raising a lot of questions that a lot of us have heard over and over again. I just want to point out a couple of efforts going on within AHR to try and help us. Many of you are probably aware there's an AHR decarbonization task force that's doing a lot of work. They published a really good kind of intro guide about 6 months ago, and they're working on a much more detailed application guide that is supposed to be published sometime in the next 6 months. I'm not a part of the project, but there is some good information out there. I am, however, leading or co-leading the effort under AHR Guideline 36 to include heat pumps in Guideline 36. Almost every one of the issues you brought up are issues that our committee members are bringing up as well. The lack of documentation, the lack of understanding for how your internal controls work are an incredible frustration across the board, and we need to figure out how to work better on that. We've brought half a dozen manufacturers onto our committee to try and help us with this issue, but it is a challenge because keep in mind, yeah, you can describe how yours works, and the designer can design around it, and then if the contractor selects a different product, you're getting back to square one. So if there is any interest in being involved in this effort, please see me afterwards. I can get you more information and get you involved if there is interest. It is an open effort, and we're really trying to find the right ways to define this. We know that these are very, very climate specific, but the questions about do you need a thermal storage, do you need a buffer tank, what happens in your defrost, should you have an emergency backup in your foot, a lot of questions, a lot we need to learn as an industry.
Yeah. We actually, on that, thank you for I was aware that some of those things were ongoing, but yeah, that's a really good overview. And we actually just finished creating a building electrification guide for retrofit applications. It's very BC specific, but one of the folks that helped create that, it's quite technical, it's a guide for consultants, but one of the folks who helped create that is on, I think, the ASHRAE 36 committee and around some of these heat pump sequences. So I think, you know, we were able to kind of take some knowledge from him and reflect that in our guide. But it's got a lot of very specific things about retrofits in it.
I think I know who that is.
So, Mike?
Yeah,
Mike.
He's saying, you know, we have specific challenges in BC because it's so cold and so damp that we're in defrost all the time.
Yeah.
So there's a lot of challenges here.
Yeah, for sure. No, and there's starting to be more resources out there. I think that's the good, like we are, and I mean, that's part of this session, right? Is like there is now, I think, enough experience in the industry that we can do a better job sharing that and actually help people avoid some of these issues. So, yeah, question.
I'm just wondering where we can get that electrification guide from BC?
You can talk to me after
It's free.
this.
And
Yeah, it's free. Yeah, you can download
Maybe
it.
the link.
If I was smart, I would have like put it on a slide that I could have showed you, but I didn't think about that for now. So, but yeah, come talk to me or Stephanie after, and we can give you the link. Any other? Yeah.
So the control too much. What are some of those items that we're trying to control so we avoid that?
Yeah. Who wants to?
I
I have opinions, but I'll hear.
was gonna say one example that I've seen is like the BAS like shutting off a unit or shutting down the heat pump once the supply temperature has been met instead of just letting the unit stage its compressors off or compressor down or whatever kind of unloading it has, or trying to force the unit into different modes too often instead of kind of trying to let that play out a little longer. So, you know, if you think about, you know, changing a reversing valve or changing a mode, it's going to be hard. You're starting a unit inverted and you got to work all the way back to getting your pressures right. I would say those are probably the two that I've seen. Temperature, sometimes we've seen some pretty erratic set point control, like continual set point reset, which seems kind of crazy. I'm not sure how, you know, really bad that could be. If it's causing more compressor cycling, it would be bad, but that'd be something I have to look into more. But really those, like enabling and disabling is one that we've seen a lot, and then the mode switching to constantly.
Brian, I think it also is that it really depends on the manufacturer too. Some manufacturers are less involved in certain parts and more involved when it comes to controls. So I really think it's super important to try and not just the mechanical side of the equipment, but then also get someone who really knows the controls, and maybe even get with the TC that you're laying out around, and kind of come up with a plan that everyone kind of feels comfortable with. Because I really do think it is manufacturer specific on what gives each one what gives Train problem might give JCI another problem. Like, it really doesn't necessarily mean just having don't do this kind of thing. I think it is manufacturer specific, and I think if you can write the spec in like a performance kind of, we want it to do this in general, and then part of it is the TC and the equipment to figure out exactly the best way to control it, instead of I'm going to turn this valve on and like that in your sequence. I think that would be helpful.
We find it hard to accept substitutes on heat pump projects because you do design kind of so specifically often to one unit, even with like system volumes and flows. And it's not like a boiler where someone wants to substitute a Lochinvar for a Viessmann. Like, that's going to be okay in some cases. But with heat pumps, you're kind of locked in to the equipment, and which has caused us problems when all of a sudden that equipment was no longer available, or they decided to switch refrigerants in between having done the preliminary design and the actual tender. So you got to watch out for stuff like that too. But anyone else want to sort of respond to Brian's question about sort of the control piece and what the do's and don'ts of DDC with heat pumps?
Well, so not so much on the BAS piece, but I think one other, along the lines of, designing one and sticking with one. I mean, I think what's important at these sites to, for us as a community to realize and plan as we, plan commissioning is, because these aren't the same boilers that we've been using for X number of years, to the site operators, it's new. And the more they have training on it, which is partially our job as equipment vendors and manufacturers of it, and our service organizations too. But the more and better they understand the equipment and the sensitivities of, hey, why isn't it at set point even though I gave it a command 10 minutes ago, and why is it bad to continuously reset that set point or continuously switch it from heating to cooling? If they understand the sensitivities of that equipment versus what the equipment that they've been used to in the plant, I think then you may have you may result in less of the issues that we kind of opened this discussion with, is that if operators understood the equipment better and there's better training on, I've got a heat pump, what do I do now?
Yeah. And specific to the controls thing, I think one other thing that we've grappled with is just like how to do night setbacks appropriately with a heat pump system. Because again, you can't go to full fire like a boiler, and they don't like low temperatures. And so, you actually end up in some counterintuitive operation where it's actually better to run at longer hours, which is like kind of counterintuitive to a lot of the energy management we've been taught. Same with heat recovery chillers. You don't want to do free cooling. Like, you actually want to keep that energy in the building and use mechanical cooling because that's a heat source for your heat pump. So there's a whole bunch of sort of relearning I find that our industry and the engineers especially need to do, to say no, these things that we've been doing for the last 20, 30 years, we got to do them differently because, again, heat pump is not a boiler. We've started recently, we were having one building where the heat pump, so we turning it off at night, it was coming on, but it was taking 3 hours to get that loop up to temperature. And then what would happen was you would finally hit a point where the boiler would kick on, but that would happen about 8 a.m. when everything else is coming on in the building, so we get these huge demand charges all of a sudden. The demand would spike in the building, we get dinged with huge demand charges. So again, a bit counterintuitive, but we're actually going to try starting with the boilers, kind of preheat, jump start the loop, if you will, with the boilers, and then let it coast on the heat pumps so that we avoid that long startup. We avoid having the heat pump having to deal with these cold water temperatures that it really doesn't like. And we're still learning stuff like that, but it takes some outside the box thinking, I think, sometimes, because we don't understand. But if we had all the information and we knew exactly how these heat pumps responded under different conditions, and the engineers actually bothered to go read all that information, I think we would do a lot better.
get a question
Yeah.
on the opposite end of the spectrum. When you're at really low load, as an engineer, I would say like provide the unit with anti-short cycle controls. How is that achieved with heat pumps when you've got those kind of like low load conditions, like shoulder seasons? And then what does the anti-recycle or anti-short cycling controls actually do? Like how should I be accommodating that?
So I'm not sure what the anti-recycle option is.
I thought it was like a anti-short cycling, so you get that really low load, there's not quite enough BTU, you hit your set point, unit's on for 30 seconds, shuts off.
I literally just say like, you have to be on for this amount of time and off for this amount of time. That's how I do that.
Is that good? But is that the BMS, or is there controls built into the?
I would say
Yes.
it depends.
Yeah, it always
The
depends.
manufacturer.
That's-
Yes.
So I think the first thing is it's important to understand that low load is certainly a concern because it's when you're asking it to generate a lot of lift and a very small amount of capacity, that's not a great point for a compressor generally to operate, right? Variable speed drives certainly help, but they're not going to give you they're only it's not you can't expect it to operate like a chiller, which could turn down to 10% with no problem because you're getting a lot of other things. You're reducing the amount of lift that it's doing. In this case, you're at full lift, full compression, but really low load. Couple reasons why we may not just want to run for a number of minutes is if you're at such a low load and I'm beyond my max outlet temperature and I'm at a pressure limit or a freeze protection limit. If I'm water sourcing, it's better for not only the safety of the equipment. If you're looking at hitting a pressure limit and bursting something, which the safety would probably hit before you even got to that point. On the refrigerant side, right? Because to make 140 degree water, you need 145 degree refrigerant that correlates to whatever PSI. If you're at a low load and you're continuing to run the compressor, that PSI value is going to go up and up and up until first you'll hit a safety and then you'll probably start blowing relief valves and whatever else. On the cold side, you'll get close to freezing and then, start bursting the heat exchanger because tubes burst. So running it for a long period of time in that low load scenario is probably going to have a drift off set point and you're going towards one of the extremes. If you know what that is and knowing the load profile is great because, there's no rule that says you have to buy, 50-ton chillers or 50 million BTU, there are 5 million BTU blocks, right? You can buy or you can design in a 1 million and a 9 million BTU boiler or a heat pump. You can design in multiple different sizes that allow you to get, utilize the plant space right, but hit your low loads, hit your efficiency targets, hit your year-round operation points that you're seeking to, hit while you're decarbonizing.
And I think the other half of it we talked a little bit about earlier, which is volume, right? Like you can always solve a lot with more volume and let your, if it's like heating, let your hot water set point kind of fall a bit, right? So maybe you don't need 120 degree water, maybe it's 100, maybe it's whatever, and you kind of let it drift off. And then when you kick it on, you raise it back up to 120. So you have that built-in load so that it can run with the volume and that extra a bit. So you kind of have a bigger sine curve, if you will, on the load. The other thing I think is it really is product specific. If you're using a positive displacement compressor, you probably have a little bit more leeway. If you're using a dynamic displacement compressor, centrifugal or whatever, then you're there's some pressure you have to overcome. It's hard to do that on that. So all of those are kind of, you really have to worry about the compressor map and all that other stuff. So it really is product specific, but having a pony system, like a small one, or volume, or letting your temperatures kind of vary based off of the load, that all different strategies that will work.
Yeah. You can create artificial loads too. You can, we'll do that to increase the heating load. Like you can say,
non-critical zones.
Yeah.
Lower temperatures.
Yeah, but then just rely on the heating system to make that up, right? Or drop your chilled water temperature to get colder water than you actually need, right? We do that a lot to get more load into the system. And yeah, you got to kind of play with it and find that balance point. But I mean, I agree, especially what James said. The system volume solves a lot of problems. It's like almost, you can't almost have too much system volume.
Does the BMS need to calculate what the BTU load is based on like volume, like flow rate?
Flow rate and delta. I mean, it's
Yeah.
good. It's good to. I know that that's not always
Yeah.
practical in every project.
Because we're talking about like, there's 2 control points we want from the BMS, like set point temperature and maintain minimum flow.
I think that kind of depends on the customer, because we see some that are just measuring temperature, improving flow, and that's fine, and while others will have BTU meters and flow meters all set up and having some more advanced controls and have, multiple pieces of equipment for staging. Like the heating turn down is one of the biggest conversations that I know that we have is, what's the minimum load of the unit, what's the minimum load of the system, and making sure that we're picking the right technology, like we talked about positive displacement versus centrifugals. That's going to be, you don't want to surge a centrifugal chiller and the customer's going to, what's going on?
Yeah.
And whereas like a screw compressor would probably be more robust in some of those applications. You guys hit it really well, actually.
Has anybody ever tapped into a wastewater stream as a source of heat?
Yeah.
Yeah.
Yep.
Yeah.
So tapping into a sewer line?
Or like a big wastewater, like a wastewater treatment plant.
Yeah.
I was just at a conference last week and I saw several presentations about that exact pulling heat out of wastewater. I think it's a genius idea. It's just, it's wasted BTUs.
If the mains are close by, it makes a ton of sense because there's a lot of heat to be gained. The other thing is on, like in the mountains, we have a lot of wastewater treatment plants that are tied to the hotel or whatever that we're serving. And so we'll sink a loop in the middle of that and try and reclaim heat from that as well.
Volume is, again, a big issue, though. I mean, we've got a school that we worked in. They put in a wastewater heat recovery, but it turned out there wasn't enough waste.
Yeah, that's the.
And they couldn't use it. So they spent, God knows how much public money on this heat pump that they can't use because somebody didn't get the system volume right. So volume is huge with heat pumps. But question back there.
Yeah, I'm just curious if you have any specific lessons you've learned on domestic hot water. I think it's a little bit more of a different animal. A lot of what talk about applies to it, but I guess
We've done a lot of domestic hot water heat pumps. And I mean, it's the big thing there, again, actually volume, but you need a lot more. Unless you're going to have a hybrid system, you need a lot of volume compared to a conventional domestic hot water. Like you just can't get the same BTUs out of a heat pump. So I mean, you can get, smaller systems are fine. Like if you've got like an office building or you're not using, but anything residential. So we've done a lot of multi-user residential ones, and they've pretty much all been hybrid systems because there's just no other way to do it. And then it's, I had one where it was running, everything was working. I probably could have signed off on it, but it was like, this boiler's running a lot more than I think it should. Talk to the controls contractor. It's like, no, we followed your sequences. It's all there. I'm like, all right, this doesn't seem right. And then I literally went through the code line by line and found one line that was sort of keeping the boilers continuously engaged. And I went back to him and said, I don't think this should be here. It's like, oh yeah, you're right. But not a lot of not a lot of consulting engineers will go through the programming code line by line. But that's almost what's necessary. And I think one of the things that we see, especially on the commissioning side, is like if you don't have somebody on that project who knows how that thing should work, and they aren't really involved, the project team is going to make a lot of assumptions, and they may not be the right assumptions. I mean, that same project, I got to the end of it, and the contractor's like, so what are these heat pumps here for? He had no idea that the whole point of, his perspective was, well, why don't we run the boiler more? Because that's cheaper. I'm like, the whole point of this is the owner is trying to get carbon savings. But that had never been communicated to the contractor. So they had no idea what they were trying to achieve with this, $500,000, very sophisticated. So of course we were missing each other, and they weren't really getting the problems that I was bringing to the table because they didn't understand what it was for. So that was a really good lesson for me. Is okay, as part of the project kickoff, I need to make it I need to go through what the intent of this project is and how it should operate. And I think that'll help solve a lot of these issues. But yeah, that's the kind of things you run into because it's new stuff and people aren't automatically going to be on the same page. I don't know, anything else about domestic hot water? I don't know if you guys do much domestic hot water systems.
I don't think I have anything.
CO2 is a great refrigerant
I mean,
for domestic hot water. We do a lot of CO2
We do a
heat
lot
pumps.
of domestic hot water. It is, I mean, if we're all just being honest, it's super pricey right now. And
Yeah.
it is, they have to really, really, really want it.
I will say the big lesson we learned too is don't rely on standard sizing calculations because they're all wrong.
Yeah.
And put a meter, and that meter, even if you spend $5,000 or $10,000 on a meter, you will that will save you so much money on the size of your system because we found. We get systems that we replaced a system that had two 600,000 BTU boilers. We're now running the system on 150,000 BTUs of heat pump with 400,000 BTUs of boilers. So we're less than half of the total capacity of what was there. Now we've got a bit more storage, but that old system was way oversized. And so you can't assume that the sizing is going to be correct. And even if you use kind of some industry standard tools, you will get sizes that are way too big. And that, I guess, another lesson we also take with all our heat pump designs is we try to use data because we do a lot of retrofits. So before we even do the project, we're looking at what the existing heat loads in the building look like. We're looking at what kind of temperatures it needs, and then using that to help inform the size and type of system that we
I was going
recommend.
to say that exact same thing, something to maybe not do. If you have a existing boiler system, say, I'm going to size my heat pump based on how my
don't do
boiler
that.
was sized.
Yeah.
I would say it's a big no-no because those boilers, I guarantee, are way oversized, and you don't want to grossly oversize a heat pump for many, many, many reasons that we've kind of talked about already. So that's, I think, a good heating lessons learned thing. Is
a
getting
BTU of
data.
gas boiler is 2 orders of magnitude cheaper than a BTU of heat pump, and that's why that's why we end up doing a lot of hybrid systems because you just can't the cost. I mean, they're already expensive even if you do it properly, and to oversize them, you just a 2 million BTU per hour boiler is not that much more money than a 1 million BTU per hour boiler, but 2 million BTUs of heat pump capacity is
double,
a lot more than a million of heat pump 1 million.
Sure.
So yeah, sizing's huge. Any other? We're almost at 2 minutes. Any more questions? All right, 2 questions in 2 minutes. Let's do it.
I've dug into a couple different manufacturers' engineering guidelines for water pumps. And both of them say, there's a number of parameters that decide based on your temperatures, how hot's the water, what's the source flow rate, what's the inlet flow rate. And then, so they also both say, but be careful not to select with any 2 of these parameters that edge in the limits. Is that pretty typical for a lot of heat pumps? Is that just how it is?
Yes.
Where,
Yeah.
okay, if I'm at the minimum flow rate on the source side, say, then I can't also be at a maximum temperature on how hot water I need.
It's all about pushing that envelope of the machine, right? And so what they're trying to do is force you back into the middle of the envelope with those comments. And so, I think it's pretty typical from what we've seen with our different manufacturers, and these guys can speak about theirs. But the idea is pushing the envelope is something that we're being asked to do daily, and we have to do our best to try and get something that is as close as we can get, but still reasonable for the equipment. And so, that's why that's in there.
Usually, especially for heating, existing heating systems were designed for 20, 30, 40 degree delta T's, and some heat pumps can do that, but most heat pumps can't do that large of a delta T. So now, a lot of times we see selecting at the highest hot water you can make at the widest delta T or the smallest flow rate the heat exchanger can take. So when you think about that, you've designed that piece of equipment on 2 edges, flow and temperature of the machine. So it's we want to try to pull that back in because we know the machine can do it, but you leave yourself little air, and you have to pump control and that kind of stuff perfectly to make that work.
Okay. we're at time. Is there one more quick question? Yeah.
Yeah. So you were talking about hybrid systems with boiler and a heat pump. We need to be able to claim greenhouse gas savings from electrification. How do we show that a hybrid system is actually going to be used as a pump primarily? Do you have any suggestions?
Yeah, I'm currently on a standards committee in Canada trying to write standards to answer just that very question. But I think a lot of it comes down to being able to demonstrate, the right design parameters where your heat pump can cover, the approach that we're taking. I mean, the problem is there's very little way to regulate a building after the system, like your permits are all closed, unless you're in a jurisdiction that has performance standards, which would be one way to do it. Like City of Vancouver is doing that, for example. They're going to have GHG performance standards that certain buildings have to meet. The only other way in my mind is really to make sure the commissioning, everything through commissioning is dialed and you've actually made sure that's happened and happened as best as you can and you've got it all signed off and you've had, at that point at least you can demonstrate that the system is operating as it should. And then after that, absent some sort of reporting, like energy reporting or emissions reporting, there's not a lot you can do that I've seen. So that's sort of the approach we take is make sure that thing is working as best as it possibly can and demonstrate that performance as part of commissioning. And then
I mean, we've all been out to
best.
buildings where the outside air dampers are completely closed, right? It's the same scenario, right? It had the ventilation when we started, but they ran into a problem and shut it. Denver's doing benchmarking, energy use benchmarking, and I think that's probably going to be pretty common across most of the U.S. To come, and they basically set what you can use and whether the amount of gas or the amount of electricity, and if you miss that, you pay a fine. And it's magical how money can kind of make things work. But that's kind of Denver's approach.
Yeah. All right, we're over time, so I'm going to cut us off. I think there's not another session here until, what time? 3:30. So these guys might stick around for a few minutes for questions, but thank you all for coming. Thank you, these guys, a hand.
That was fun.